We're moving from treating LLMs as external APIs to operating inference as managed infrastructure. That control layer unlocks routing, caching, fallbacks, observability, and cost accountability, making GenAI systems cheaper, more reliable, and easier to scale. Module 1 gave us the diagnosis. The system did not fail because the model was bad. It failed because the architecture could not control cost, latency, overload, GPU memory pressure, or behavior changes over time. That is the shift for Module 2. Every failure mode becomes a design requirement. Token cost pushes us toward batching, routing, and quantization. Timeouts require better serving and fallback paths. Drift requires observability. Now we move from troubleshooting a fragile GenAI app to designing a reliable LLM serving platform. The first change is ownership. In the old model, each product service calls an LLM API directly, so operational concerns are scattered and often invisible. Latency, retries, cost spikes, quality drift, and provider outages all appear as application problems. In the new model, inference becomes a shared platform capability. Product teams send requests to a controlled layer that handles routing, caching, fallback, budgets, and monitoring. Reliability and cost can improve centrally, without rewriting every service that uses AI. In this architecture, product teams stop integrating with individual models directly. They call one stable model gateway. The gateway becomes the control point for policy, caching, routing, and safety decisions. Predictable, high-volume requests can go to a self-hosted vLLM cluster. Requests that need premium capability or need a backup path can fall back to a commercial API. Around that flow, shared services record metrics, attribute cost, and support reliability. The result is flexibility without every application owning model orchestration. Think of the model gateway as the control plane for every LLM call. Applications send one standard request, and the gateway decides what happens next, which model to use, whether the tenant is within limits, whether a cached answer is available, and how retries or fallback should work if a provider fails. Product teams no longer wire directly into OpenAI, Google, AWS, or any other API. More importantly, cost, reliability, logging, and governance rules are enforced in one place, so behavior stays consistent across features. The core design principle is separation of concerns. Application services should describe what they need: the task, latency target, quality tier, and tenant context. They should not decide which GPU, replica, batch, or provider handles the request. That belongs in the serving plane, where infrastructure can optimize utilization, route around unhealthy models, scale capacity, and change providers safely. This boundary lets product teams move quickly without owning inference plumbing, while platform teams improve performance and reliability without forcing every application service to redeploy. A production request should not go straight to a model. It first becomes a normalized request. Who is asking, what task is being performed, how urgent it is, and what quality level is required. The gateway applies policy, budget, rate limit, and cache checks before spending tokens. If inference is needed, routing logic chooses the best path: self-hosted model, external API, or fallback provider based on rules and current health. Every outcome is logged with tokens, cost, latency, traces, and model version, so the platform can improve safely. Smart routing starts with structured metadata, not a fixed endpoint. The gateway needs to know the task, expected prompt and response size, customer context, and risk level. With that information, it can make practical trade-offs: cached or local models for tight latency, stronger models for premium or high-risk work, and lower-cost models when quality needs are moderate. The goal is simple: enforce policy consistently without wasting expensive inference capacity. Semantic caching happens before the model is called. The gateway decides whether the request is safe to cache, then normalizes it, embeds it, and searches for nearby prior requests. If the match is strong enough, for example, a cosine similarity above 0.92, the system returns the stored response instantly. If not, it routes to inference and may save the new result. The key trade-off is threshold design. Too loose creates quality risk. Too strict leaves savings on the table. Store the model version, TTL, validation metadata, and prompt signature so cached responses remain controlled. A practical hybrid strategy starts with self-hosted models because they are well suited to predictable, high-volume, cost-sensitive work. You control latency, data handling, and unit economics. But not every request should stay there. Some prompts are rare, ambiguous, safety-critical, or require a higher quality ceiling. That is where commercial APIs still matter. The gateway hides provider differences and applies routing policy consistently. If confidence, capacity, or safety drops, traffic can shift without changing the application. Hybrid inference is not compromise. It is resilience and cost control together. Fallback should never mean try everything until something works. Start with the preferred model, but give each request a strict timeout and retry budget. If the same pool looks unhealthy, a circuit breaker opens and stops sending more traffic there. From there, move through tiers intentionally. Another local model, a commercial API, or graceful degradation. Each step should match business priority, quality expectations, and cost limits. Finally, log every fallback, timeout, and breaker state change. Those events show whether resilience is working or quietly turning into expensive outage amplification. Every LLM request should carry a trace from the product service through gateway policy checks, cache lookup, model generation, response handling, and any fallback route. That trace turns a vague complaint like the assistant was slow into specific evidence. Latency by span, token volume, cache hit rate, provider errors, fallback frequency, and model version. Structured logs connect user-facing failures to infrastructure behavior. Standardizing this with OpenTelemetry-compatible instrumentation keeps teams from inventing one-off dashboards and makes cost, quality, and reliability visible in the same operational language. Cost attribution belongs in the architecture, not in finance cleanup after deployment. Every request should carry metadata: tenant, feature, endpoint, model, provider, and token counts. That connects spend to actual business activity. Instead of asking, why is the LLM bill high? Teams can ask, which workflows cost too much per successful task? Once cost is measured at that level, it becomes actionable. The system can route simpler requests to smaller models, improve caching, adjust prompts, or justify premium models where the unit economics make sense. The target architecture is also an operating model. Product teams own the business behavior, what users are asking for, and what good responses mean. The platform team owns the shared mechanics: routing, model serving, reliability, and cost controls. These concerns should be deployable independently, so a model upgrade, routing rule, or cache policy can change without disrupting product releases. Slows make the system measurable. Latency, availability, fallback rate, cache hit rate, and cost per request. Telemetry closes the loop, turning real usage into better routing, capacity planning, and cost decisions. You now have the target architecture for reliable, cost-optimized LLM serving. The core idea is separation. A model gateway governs traffic, policy, cost, retries, caching, and fallback, while the serving plane scales inference independently. Hybrid deployment balances self-hosted efficiency with API flexibility. Next, we'll turn this blueprint into implementation, starting with choosing and fine-tuning open-weight models.